Okay, guys, welcome. I hope it's recording. So let's start with actually the first chapter. Okay, I want to ask you something. Did you get emails from me? Okay, so did you subscribe to my newsletter? Okay, so anyone who didn't, maybe, I apologize. So maybe if you didn't, then I'm going to write down my email address again. Okay, so maybe somebody's watching it right now. Okay. And he or she is not aware to actually how to register. Okay. So this is my email address. Okay, so please send an email if you haven't already, and then I'll put you on the list. Okay? So you got all the information that actually you might consider. Lecture notes, examples, stuff like that. Okay, good. By the end of this week, I'm going to publish the first assignment, and yeah, I would like you to read very carefully how to submit. Okay, so then you're supposed to be grammar. In 2 days, I'm going to say more information to that. Okay, good. Now let's start with the propositional calculus. Okay, so this is going to be the first chapter. Okay. Or you can also say propositional logic, it doesn't matter. Okay? So this is about actually logic, guys, to put it simple. It's about statements, and just let me give you actually the first definition. So statements are either true or false. Okay? So statements are actually sentences that are either true or false. Okay? So are either true or false. Okay. And expressions true or false, these are the so-called truth values of a statement. Okay, so truth value, sorry. Okay. Okay. So the truth value or truth values of a statement is either true or false. Okay, so when any statement can be assigned to a certain value, maybe true or false, is a statement here according to the setting. Okay, so for instance, let me give you an example. Okay, so maybe I've seen this here. So for instance, if you say like something like, you know, the weather is nice or whatever, okay, which is actually true. Okay, all right. Sorry. Is nice, okay, then this sentence does not constitute a statement here in this setting, okay? And the reason for that is because you cannot define the word nice. It's not possible, okay? So we don't know what it is. I mean, nice for who? For what? And for what? This is actually what the question is about, okay? So if it's sunny, then it's nice. For what? And if it's raining, it's not. Okay, but without rain, you would not survive. So that's the point. I mean, the question is nice for who and for what? Okay, so this is not clear here. in that case, so okay, so that expression, nice. What is nice? Okay, I mean, this is not obvious. So here in that case, you know, what you have is that this is not a statement. Okay, so it's not a statement in that sense. Okay, so of course, although you might consider that expression here to be true right now, okay, suppose, okay, but there is no definition of the word nice, so in that case, it cannot be regarded as a statement. But on the other hand, for instance, you can say like, I mean, if you say something like Frankfurt, okay, is larger than Munich, okay. Okay, then in that case, this is a statement which is here in that sense, which is false. Okay, so in terms of, you know, inhabitants or whatever, or the area, I mean anything like, you know, Munich is larger than Frankfurt, of course, but here this is a statement. Okay, so this is a statement, although it's false. Okay, you understand? Okay, so here on that concept, the truth value of the statement is false. I mean, the statement in itself is not false. Okay, so that expression that it is a statement is not false, but the truth value, okay, is false. You understand? Okay, so that's a distinction that I'm making. All right. Is it something that is clear here in that case? So it can be a statement although it's false. So just because it's false, do not assume it cannot be a statement in the logical sense. Okay, so we're only talking about statements in the logical sense, guys. We're no longer talking about, you know, other sentences that are actually no statements here in that sense. Okay? All right? Can you read this? I mean, after I read myself, so sometimes I cannot read my own writing, so just tell me if it's not possible, okay? Good. Now, first, I mean, let me continue here, and this is going to be the next definition. So what we have is, or are so-called logical operators, okay? These are not the only logical operators that we consider. I mean, but there exists, sorry, but these are the most important ones that we consider. Now, first off, the most important logical operator is the disjunction. Okay, so this is called disjunction. Okay, so that's the first one, and the notation for that is this. So suppose that A and B are statements. And we have that A or B, this is actually the inclusive injunction, okay? So you also say statement A or statement B. Okay? Maybe you heard that. This is the so-called inclusive disjunction. It doesn't mean that you say either A or B, okay? So in the logical sense, we're going to look at the true values of the statement, okay? So please note that the disjunction, what we have here, A or B, this is the notation for that, is a statement itself, okay? So if you perform that operator on these two statements, then what you get is a statement, okay? So nothing else, all right? Now, then you got the so-called conjunction, guys, okay? Conjunction, okay? This is the AND operator, so you can also say logical AND. Okay, so it's denoted like this. Okay, so this is the triangle, and if you see this, then you can just say A and B. So please assume that A and B are statements, and what you actually say here, if you see this, then sorry, I have to put the quotation marks up there. Okay, that's grammatically wrong in English language. So you say A and B. I apologize for that. Okay. So that's the conjunction. All right. Okay. So this is another operator, and as it's the case here, if you perform that operator in two statements, then what you're going to get is also a statement itself. So A and B is going to be a statement. I'll give you an example for that later on, so you can see. All right. Now, then you have the negation, okay? And the negation is written like this, that corresponds to the complement of a set. So if you look at set theory, then this could be the complement. Okay, so this is how it's written. And you just say not A, okay? So that means that statement A is not true. This is what you say. And that of course, is also a statement itself, right? So if you have a certain statement like, for instance, Munich is larger than Frankfurt, and then you say not A, which means that Munich is not larger than Frankfurt, then you have a statement itself. So that means that the statement A is not true. Or you can say, A is not true. Okay, so something like that. Okay, which is a statement itself. Okay, so depending on the context, how you turn it around. Okay, do you understand that? Okay, and the last one that I will consider here is the so-called implication. Okay, so the logical implication. Oh, sorry. Okay, and the notation for that is this. Okay, so you see, let's assume that A and B are a statement, and you want to say that A implies B, so this is an implication, then you write it like this, okay? All right, so here you can say that A implies B. You understand? Okay? So this is, or these are, let's say, the most important ones, okay? And that is, of course, that the statement that A implies B is actually a statement itself. Okay, so I'm going to give you examples of that, but let's just have a look at the truth tables of these operators. Okay. All right. Okay. Is this clear? So let me just look at, for instance, the truth value. Okay, so of the conjunction and the disjunction itself. So suppose that you have statement A and statement B, and then you have let's consider the disjunction first, and suppose that statement A is true, and suppose that statement B is also true as well. Okay, so what about the disjunction? Is it true or false? And what? Yeah, true. It's true, okay. And what about, let's say, suppose that statement A is false, statement B is true. What about the disjunction? In that case, yes?
True.
Yes, okay. And for instance, statement, sorry, no, let's do it the other way around. So suppose that statement A is true, suppose statement B is false. And what about the disjunction? Yeah,
it's true.
It's also true as well. And suppose that both statements are false. So if both statements are false, then the disjunction is false, right? So this is the truth table of the statement. There are actually 4 combinations if you assign two truth values to each statement. Okay, so then you get 4 combinations. And you can say that here, it's clearly what you have is that the disjunction is false if and only if both statements are false, right? So this is what you see. For instance, let me give you the following statement. 0 is less than or equal to 1. Okay, so some people say that this statement is actually false, but 0 is less than or equal to 1 means that either you have 0 is less than 1, or, okay, so just write like this, or 0 is equal to 1. Okay, now of course, here you have that 0 is less than 1, which is, this is a true statement, and that is of course a false statement, but the combination of the two, if it's performed by the disjunction, is going to be true, right? So 0 is less than or equal to 1, guys. Okay, I would like you to know that because sometimes people get confused, all right? Okay, so this is a true statement. So here in that case, since both statements are equal, let's say equivalent, I'm going to define what equivalency means. That statement is also true as well, all right? You get that? And let's consider, for instance, also the truth values of the conjunction. So this is the logical conjunction here. So what you got is, for instance, if A is true and B is true, then of course the conjunction, the conjunction is also true. All right. If A is false and B is true, then the conjunction is false. Clearly see. So in that case, both statements have to be true in order for the conjunction to be true. All right? Okay? Just let me just continue. Suppose that A is true and B is false. Okay? So then A and B is also false. All right? And suppose that both statements are false. So if both statements are false, then the conjunction is also false. This is quite obvious. All right? And I would like you to actually to note that. All right. I think it's as clear. Okay? So for instance, let's say that, suppose that, just let me give you an example. A is less than or equal to 2, and A is greater than or equal to 1. Okay? So here in that case, if let's say A is a number and it is less than or equal to 2, and at the same time it is greater than or equal to 1, then of course this means that the number X is between 0 and 2, 1 and 2. Okay? So this is equivalent in that case. Okay? I'm going to define what equivalency means, but this is actually the same thing. Okay? You understand? Okay? So here in that case. Good. Because that statement here, all right, so this statement is true if and only if that statement are true. Okay, so these both two statements are equivalent, but I'm going to define what actual equivalency means. Okay? All right, is this something that is clear? Okay, so you have to be aware of that because I'm going to referring to these things, and I would like you to remember what a conjunction, what a disjunction, etc., means. All right? Okay? So let's have a look at, for instance, at the negation. Suppose that statement, so this is going to be the next. Suppose that statement A is true. So then if statement A is true, then its negation is going to be false, obviously. And if statement A is false, then its negation is going to be true. Okay? That is also obvious. Okay? All right. So for instance, if, let's say, a certain number is not less than 2, then this means not less than 2 means what? X is what? Greater than or equal to 2, right? So that's the same thing. Okay? All right. Okay, so this is not a binary operator we had in here for in these cases. So here the disjunction and the conjunction, these were binary operators. Okay, but the negation is not, because the negation is performed only just in a single statement. All right. So that's why you only have just 2 possibilities for the outcome. All right. Okay. Now let's consider the implication as well, guys. And for the implication, it's going to be a little more interesting. Okay, so because I'm going to give you right now the following definition. So suppose that we have the following statement which is true. Okay, suppose that A implies B. Okay, so suppose that this statement is true, right? Okay. So we assume that here in a moment. Okay, you're going to get an example for that as well. So then what? Then what you have is that A is called a sufficient condition for B. Okay, so A is called sufficient, all right, for B. Okay, so this is the word that I'm defining here. Or you can also say sufficient condition. Okay, just I'm going to write sufficient for short. And B is called necessary. Okay, so this is something that is also very important, guys. Okay, so if A implies B, you can also say that A is sufficient for B, or you can say B is necessary for A. It doesn't matter. Okay, and now I'm going to give you an example for that. Just please make some notes, and then I'm waiting for you to just write it down. We consider an example to this. Okay, so what is actually necessary and sufficiency and necessity means here in this context, okay, from the logical perspective. But this is actually the same thing as you say, if A implies B, then you can say A is sufficient for B, or B is necessary for A. It doesn't matter. Okay? Let me give you just an example for that. Okay? All right. Can I continue? Because I need to have a new slide here. Okay? All right. So save it and just move to the next. Okay. So let me just consider the following example to that. So suppose that, for instance, you already know that if a number is divisible by 6, then it's going to be divisible by 3. You already know that, right? So any number that is divisible by 6 is also divisible by 3. Okay, let me write this down. This is a statement that is true. So any number that is divisible by 6 is also divisible by 3. So that is obvious. I hope that this is nothing new for you guys, okay? No intellectual challenge, right? Okay, I hope you understand this. Okay, so what does it mean? It means that actually if you want to denote this from the logical perspective, you can also say that the divisibility by 6, okay, so if a number is divisible by 6, so it's all right for short, divisibility by 6, okay, in German you say Teilbarkeit, okay, so maybe that is clear, implies the divisibility by 3, all right, okay, so, and this means, I mean, you can say that divisibility by 6 implies divisibility by 3, so which means that also that divisibility by 6 is sufficient for divisibility by 3, right? Okay, so any number that is divisible by 6 is also divisible by 3. And on the other hand, you can also say that the divisibility by 3, here, this statement here, is necessary for the other one. Okay, so that statement is a necessary one. And this statement is a sufficient one, okay? So that statement here is necessary, okay? For the divisibility by 6, okay? For divisibility by 6. Why is that? Because if a number is not divisible by 3, then it cannot be divisible by 6. You understand that, okay? And this statement here, on the other hand, here, this one, on the left, this one, is sufficient for the divisibility by 3. Okay, so this statement is sufficient. Okay, apologize. I'm using different colors so you can identify it. Okay, so this is sufficient for the divisibility by 3. Okay, so if a number is divisible by 6, then it's going to be divisible by 3. You understand what I'm saying? Okay? So that's actually the same thing, guys. Okay? Now let's just give you another example. Okay, so maybe you can, use that in your own language. I remember Arnold Schwarzenegger saying the following thing. I say it in German because he said it in German. He said, when he was training, he said that, wenn es schwabbelt, dann ist es fett. Okay, so that means if it jiggles, okay, so this is another example, okay, what you're laughing at. That statement is true, right? So, or let's say, assume that this is true, okay, so assume that, okay, so let me put this in quotation marks, if it jiggles, okay, then it is fat, okay? All right? So let's suppose that this is true, okay? So what does it mean from the logical perspective, okay? So anything that jiggles, okay, so if you find something that jiggles, then it's sufficient, then it's going to be fat. On the other hand, if it's, so for something to be actually to jiggle, it's necessary to be fat, okay? Because if it's not fat, then it doesn't jiggle, okay? You understand? All right, so here, for instance, in this case, sufficiency Okay, so what is sufficient for being fat? Okay. So sufficient for being fat, it has to jiggle. Okay. Okay. And what is necessary to jiggle? Okay. Okay. Okay, so let me just write it like this. So here in that case, it has to be fat. Okay. You understand? Okay. So this is an example in real life. See what I'm saying? So, okay, so you can say that, but just because it's fat, it doesn't mean that it jiggles, right? So it means that being fat is not sufficient to jiggle. Understand? Okay, so for instance, coconut oil. Maybe you bought this from the retail store or whatever. Okay, so you can cook. If you buy coconut oil, okay, so for cooking, then it's solid, guys. Okay, so the state of matter of coconut oil is solid. Okay, so in German, I'm not sure if you can buy this in America or what, because I haven't seen that, but in German you can buy Kokosfett. Okay. Okay. So Kokosfett or coconut fat or whatever, I'm not sure, is solid, guys. Okay, so the state of matter is solid, or the same thing for butter. Okay, so butter is also fat, let's say to 95% or whatever. So, but it doesn't jiggle, right? So just because it's fat, it doesn't mean it jiggles. But if it jiggles, then it's fat. So you understand the concept. Okay, so being fat is not necessary. It's not sufficient to jiggle, but only necessary. And on the other hand, if it jiggles, then it's sufficient, but not necessary for being fat. Okay. Okay, so you can understand that hopefully. All right. So this is just an example. So you cannot turn that statement around in the logical sense. So there is one statement which is sufficient and one statement which is not necessary for the other, but you cannot switch that. Okay? So any statement, in case you can switch that, how do you actually refer to a statement if you can switch them? So if you have, let's say, suppose that you have, for instance, two things. Okay? So let me define this because this is important. Okay, so suppose that you have that A implies B and B implies A at the same time. Okay? So here in this case, you have that both A and B are sufficient and necessary for each other. Okay? You understand? So in this case, how do you refer to that fact? So then what? Then A and B are called what? Yeah? Equivalent. There you go. Okay, so then the statements are equivalent. Okay? So here in this case, if both statements A and B are both sufficient and necessary for each other, then they're called equivalent. I hope you understand this. Okay? Alright? So, for instance, here the notation for equivalency is actually clear, right? So both, if let's say A is sufficient for B, and B, you want to say that B is sufficient for A, and this is actually just, this double arrow here, so left and right arrow you can see. Okay, so this is a sign for equivalency. You already have seen this before, probably. Okay, but you see this a lot of times in the lecture notes as well, so maybe then you recognize that you see an equivalency here. Okay, so if you, let's say for instance, if you want to prove the statement that A equivalent to B, so for instance, maybe you get this in assignment or what, okay, so that could be your topic, and you have to show the equivalency, and this is something what actually somebody didn't consider. Okay, so suppose that you have to prove, just let me give you an example. Okay, but let me give you an example first. So for instance, if you see that if a number is divisible by 6, then what? Then it's divisible by, let's just construct an equivalent statement. So divisibility, okay, so many I's, okay, by 6 implies, on the other hand, divisibility by what? By 3, And how would you actually construct two equivalent statements, okay? Because divisibility by 3 is just necessary but not sufficient for divisibility by 6. So just because a number is divisible by 3, it doesn't imply that it's divisible by 6, of course, right? Okay, so how would you actually extend this to get an equivalent statement here, guys? How would you do that? Yes?
Putting n statement divisibility by 2.
Yes, okay, so divisible by 3 and 2, right? Okay, so you have two things. So if a number is divisible by 6, then what? Then it's divisible by 3 and 2, all right? And if it's divisible by 3 and 2, then on the other hand, it's also divisible by 6. So you find that these two things are equivalent to each other, okay? Because one statement implies the other and vice versa, all right? So, you know, I mean, they are both sufficient and necessary to each other, all right? Okay, so this is actually obvious. So here you have two equivalent statements, okay? And the statements before we've also considered were also equivalent, okay? So for instance, you have that 0 is less than actually equal to 1. That is equivalent to that 0 is less than 1 or 0 is equal to 1. So these two are equivalent as well. Okay, so what I mean is this. Okay, this is the equivalency sign here. Okay, is this clear, guys? Okay, so here you have actually two examples. Now, two statements are equivalent if they both have actually the same truth tables. Okay, so if you want to show that two statements are equivalent, all you need to show is actually that the truth tables are equal. That's it, okay? I'm going to demonstrate that here in the next section, so you will going to see this, okay? Now, but suppose, I mean, the problem with this is the following. Suppose, I mean, you see this. Suppose that you need to prove that, suppose you need to prove that a certain statement is equivalent to another. Okay, so then this proof consists of two parts, and let me just remind you that because you know sometimes people tend to forget this, and you might need this for your paper or whatever if you choose to present something and you have to show some equivalency or whatever. Okay, so then this proof consists of two parts. Okay, so the proof you need to show actually two things. Okay, consists of two parts. Okay, now the first part, you need to prove that A implies B. Okay, so that's the first thing you need to prove. And the second part is that you need to prove that B implies A. So, and then only after that, you have shown that the two statements are equivalent. And you need to show both things, okay, not just one. Okay? Alright, so if you just show one, then you only get 50% in total. I hope this is clear, okay? And I don't want you to fail, so you should be aware of that, okay? Now, how would you recognize from, let's say, from a certain perspective? I mean, if you read something, how would you recognize, let's say, for instance, sufficiency, necessity, or equivalency? How would you recognize that? Okay, so let me give you an example to that as well, okay? So, for instance, suppose that you want to say that A is sufficient for B, okay? So what you actually see in the text, for instance, I put this in quotation marks, if, let's say, if A, so if statement A is true, then B, so this is how it's denoted, okay? Okay? So if a number is divisible by 6, then it's divisible by 3, okay? If it jiggles, then it is fat, okay? So that's how you refer to that. So here in that case, if you see something like that, or read whatever, or hear, then you should actually identify this to be an implication, which means that statement A implies B, or you can say statement A is sufficient for B, or on the other hand, you can also say that statement B is sufficient for A. You understand? Okay? Now, on the other hand, I mean, this is actually how you express sufficiency in in a regular language, but you can also express necessity somehow So you can say only, I mean, this is what you say. So only A if B, okay? All right. So that means that B is necessary for A, which is actually the same thing, okay? So if, let's say, B is not true, all right, then statement A cannot be true as well. Okay, so that's how you recognize if somebody says B is necessary for A, okay, which is the same thing as you say A is sufficient for B, all right? Now, how would you recognize equivalency? You recognize equivalency if someone says A if and only if B, okay, so this is how you say it, okay? So if you want to express, for instance, you know, these statements above, I mean, just let me show you for a minute. I'm going to give you time just to note this, or sometimes people are kind of lazy and they write something like this. This is not, okay, so this is not very common, but sometimes you see this in the literature. I think it's a scandal, but anyway, so let's say A, if, and you write, you know, if like using a double F. So if, by writing a double F means that if and only if, okay, but this is something that only mathematicians know, okay, so do not, I mean, just don't be surprised, okay, so please do not use this in your seminar paper, okay, because I'm kind of sick of that when I see this. It's not accurate, okay, so A, if and only if B, okay, this is short, you know, the short version, but this also denotes equivalency, okay. All right, okay, but let me just demonstrate that. So for instance, if you want to say, for instance, here in these two cases, okay, in the regular language, that this statement is equivalent to this one, okay, how do you say this? So you can say any number, a number is divisible by 6 if and only if the number is divisible by 3 and 2. All right, so this is how you say it. Or you can say actually the other way around, a number is divisible by 3 and 2 if and only if it is divisible by 6. Okay, so that's how would you recognize equivalency. Okay, so sometimes I'm not using formal language to denote, for instance, a certain lemma. So here in that case, you have to recognize for yourself that it's going to be an equivalency, and then you have to show, in that case, for the proof, you have to show that, you know, one statement implies the other, and also the other way around. Okay? So this might be a criticism that you might get. So I would like you to be aware of this. All right? Okay? Does it make sense? Okay? So that's how you recognize it. I mean, I suppose that you already know this, but anyway. Okay, now let's look at certain properties that these things have. Okay, so for instance, and this is going to be a remark, okay, because I would not classify that as actually to be a lemma. Okay. Now the first property that, for instance, the disjunction and the conjunction have is that they are both commutative and associative. Okay? So the first property is commutativity. Okay? Commutativity. This is how you say it in German. Okay? So what does it mean? It means that if, for instance, let's say you have the statement A or B, and suppose that this is true, then it's going to be equivalent that B or A is also true, and vice versa. Okay, so you can say that A or B is true if and only if B or A is also true. That should be clear. And the same thing holds for the conjunction, guys. Okay, so the conjunction of two statements A and B is also true if and only if the conjunction of the statements B and A is also true. Okay? And vice versa, the other way around. Okay, so it's actually clear. So this property called commutativity, guys. Okay? Okay, so you say that the disjunction is commutative and both the conjunction as well. Okay? Now, you also have associativity. Okay? So associativity means that you can use parentheses wherever you like. For instance, suppose that you perform this operator multiple times. Consider the junction first, so you have A or B or C. This is equivalent to the following statement, namely that you have A or B first, so you have the conjunction, the disjunction of A and B first, and then you perform on that statement, you perform another conjunction on statement C. So this is the same thing, and you also need to be aware that also associativity means that you can, you can use parentheses or you can leave them. This is actually up to you. So either you neglect them or you use them. It's up to you. Okay, so this is the same thing as to say that you have the conjunction of A and the statements B and C. Okay, so that's the same thing. Okay, so this is what associativity means. You have this, for instance, also for addition as well. So additivity, and then you have it for addition, multiplication, but also associative, and this operator is also associative as well. Okay, and the same thing holds for the conjunction too. So you have A and B and C is equivalent to A and B, right, and C, and you have another equivalency here, so A and B and C. All right, so this is also true for the conjunction. So you say here in this case that the conjunction is associative. Okay, so both disjunction and conjunction are associative. All right. Okay. Now the third property that I would like you to consider is the so-called idempotency. Okay. This is easy. So, for instance, suppose that you perform these binary operators on two statements in which actually the statements are equal. So suppose that you perform the disjunction on a statement for itself. Okay? So if you say A or A, right? So this means that this is true if and only if statement A is true. All right? So that should be clear. Okay, so here in this case you say that this operator is idempotent. All right? So the disjunction is idempotent, which means that if you perform it on the statement itself, then what you're going to get is a statement, because these two things are equivalent. Okay, same thing holds for the conjunction as well. So you say that the conjunction is also idempotent here in this case. Okay, this is something that you don't have, for instance, for the multiplication, right? Because the multiplication is not idempotent. So for instance, 5 times 5 is not equal to 5, right? Okay? Sometimes it works. 1 times 1 equals 1. But, in general, it doesn't work. So you say that the multiplication is not idempotent, but the conjunction is, and the disjunction as well. Okay? Okay, I hope this is clear, and you need to be aware of this. Okay? I'm going to continue here, guys. Okay, so this is the third property, and I have actually enough space to denote actually the fourth one. You have the so-called distributivity, all right? So that property refers to actually to something where you mix up the two things, okay? Here in terms of logic, you have two distributivity laws, namely the following. So A, you can say A or B and C is the same thing as, and you can apply this. You remember this from number theory. So you have A times B plus C equals A times B plus A times C, and here you're going to have the same thing. Let's say analogously. So you have A and B or A and C. Okay, so this is how it applies. And here in this case, you actually do distributivity laws. Namely, the second one is as follows. You have A and B or C is equivalent to A and B. No, I made a mistake, guys, here. Sorry, I mixed it up. I apologize, I made a mistake here. So this is complete nonsense. No one recognizes it, okay? How come? Anyway, so here you have A or B and, A or C. Okay, so this is it. Okay, so that's how it applies. Okay, so if you refer to that as, you can see, A times B plus C, then you have A times B plus A times C, right? Okay? And here for this statement, it's the other way around, because there exists actually two distributivity laws. So you have A and B here, all right? Or, and then you have A and C. Okay, so this is actually how it works. So here in this case, in propositional logic, you have actually two distributivity laws instead of one. For numbers, you only have one, but actually for logical statements, you have two. Okay, same thing for set theory as well. Maybe I'm going to repeat this so then you see the analogy between the two. Okay, so because set theory closely relates to actually to propositional calculus and vice versa. All right, so these are the things that you need to be aware. And if you want to examine, for instance, if statements like that is true, then if this statement is true, if and only if this statement is true, and the other way around, of course. So here for that, the same thing. Okay, is this something that you are aware of now? Okay, I'm not going to consider any examples. You will find that in the assignments. Okay, so there I'm going to give you assignments to that. So then you're going to see it there. Okay, but you need to be aware how it goes. Okay, guys. Okay, so then I would like to continue. Okay, so for instance, okay, and let me just give you the following lemma, which is very important. Okay, but maybe just before that, let me just continue with certain properties that actually not part of the lecture notes, but supposed to be there. So this is going to be a remark. What happens, for instance, suppose that you have a statement, okay, and you perform the negation operator on the statement twice. So what do you get in this case? So you say something like not the negation of A. So what does it mean? Okay, so it's equivalent to what? Yes,
to A?
Yes, exactly. So this is the same thing, guys. Okay? It's not in the lecture notes, so that's why I would like you to actually to be aware of it. So if you form that operator twice on the statement itself, then actually it cancels out, so this is what you're going to get. All right? Good. Now, the next thing here, the next proposition is going to be important, guys. Okay? Because you can apply this for proving the following thing. So I'm using the formal notation here, guys. So for instance, what you have is this. So the implication of A and B, so A implies B, is true. Okay? So this is true if and only if the following statement is true. If not B implies not A. Okay? So A implies B if and only if not B implies not A. Okay? So for instance, suppose that you want to show that statement A implies B, you can do this by showing that not B implies not A. You understand? So for instance, let me go back to the example that we were considering here before. So just let me demonstrate this. So then you see the equivalency, because it's very easy to prove that this is true. Okay, so for instance, what you have is, I take the example with the divisibility. Okay, so let's just consider that again. So if a number is divisible by 6, then it's divisible by 3. Okay, and assume that you wish to prove that statement is true. Okay, so you want to prove, for instance, that any number is divisible by 6 is divisible by 3. Now here you have the option that you can show that it's actually not to show that if a number is not divisible by 3, okay, so if that statement is not true, all right, then the other statement cannot be true either. You understand? Okay, so this is equivalent to, and let me just denote this, like I'm using the following thing. So I put this in parentheses and I'm going to express this as the following equivalent statement, which is actually equivalent to the following. So if that statement is not true, okay, so let me just write it like this. So if divisibility by 3 is not true, then this implies that the number Okay, so if a number is not divisible by 3, then it cannot be divisible by 6 either. You understand? Okay, so then the other statement is not true either. Okay. Okay, which is actually easier to show. Okay, so you only have to find an example where you actually break this up. So if it's not divisible by 3, then it cannot be divisible by 6, which is actually more obvious here in this case. Okay, so because if it's not divisible by 3, then the remainder of the division is not 0. So if the remainder of the division by 3 is not 0, then the remainder of the division by 6 cannot be 0 as well, which is quite obvious because 6 is a multiple of 3, right? So showing that statement from this way around is actually easier, and then you have automatically in that case, all right. So then you have automatically shown that the divisibility by 6 implies divisibility by 3. Okay, using that, and that actually follows from this statement. Okay. That's why you have that B is a necessary condition for A, because if B is not true, then you have that A cannot be true either. Okay? And guys, this is very important. Okay, so each time you want to show a certain statement, to turn it around, then you apply this formula. Okay? I'm going to give you later on. This will refer to example number 1. Okay? And this is going to be very important, so that's how you examine in most cases if a statement is true or false. Okay, now let me just continue, guys. You have another lemma here, okay, which is important. So this is going to be the rules of the Morgen. Maybe you heard that as well. Okay, so these are the Morgen's. These are going to be the Morgen's laws. Okay, and they go like this. Okay, so there are 2. The first law applies as follows. Okay, so the first law is the negation of the disjunction of 2 or more statements. Okay, so the negation of the disjunction is what? Is equivalent to the conjunction of the negations. All right? So that's how you break it up. Okay? Again, the negation of the disjunction is equivalent to the conjunction